cricket. Okay. So if you want, you can try to measure these loud sounds that he's making. This lasts for 6 seconds. If someone wants to count, then you can calculate the temperature and compare to my result. So I'll put again, if someone is interested to count each chirp. It will be fast, so be careful. Okay. So I will start with some interesting facts about the crickets. There are lots of species of them. There are 900. It's a lot. They are nocturnal animals, so that's why you listen only to them during night. And how do they make this chirping sound? That's interesting. Let's start by seeing a picture. If you can see that there is the wings are transparent, but there are these more dense parts that are really some teeth that they scrap on the other wing and produce the noise. We can see a video. I recommend the most sensible not to watch this video. Some people don't like insects, so you can see how the wings scrap each other and produce the noise. Okay, no one was disgusted by the... Crickets are cold-blooded. This is important because they take the temperature of the environment. We don't. That's why the winters here are difficult for us. They mate in late summer. This is just an additional information. That's why they are more loud in the summer, because the chirp works as a mating device, if you can call it that way. So how you determine the temperature is using this law. I know some of you like to think in terms of Fahrenheit, so I put the two scales. So use these formulas. And the first thing we should do is to check if it gives reasonable results. This formula was published by Dolbear 1 century ago in an article. Actually, these formulas are just for one species of crickets, because we need that your crickets chirp. Only the frequency only depends on temperature, not on other characteristics like the age of the cricket. And for other species, it may depend on the age of the cricket. So using these formulas, and I counted 20, I call it creased loud sounds. I counted 20 in 6 seconds. So I should have said that formula, the n is the chirps in a minute. So you must multiply this by 10. And I got 33 degrees and 90 Fahrenheit, which is reasonable for a night in summer Australia, where the sound I showed you was taken from. So why this law seems to work? Why is there this law connecting the frequency of the chirp and the temperature? So the mechanism they use, the crickets, is they use the muscles of their wings to produce that movement. And the contraction of muscles are controlled by chemical reactions. So chemical reactions are also quite dependent on temperature. So this connects the two concepts, the frequency of the chirp to the temperature, through the chemical reaction. So let's dig a bit more on this subject, the rate of a chemical equation. So the rate of a chemical reaction is defined by that. It's how fast you are consuming your reactants. It should be proportional to the concentration. If you think of it microscopically, to have a reaction, you must have the collision of the reactants. And the more there are per unit of volume, more likely are those collisions. So this part is trivial to understand. The other part has a temperature dependent, and is called a Arrhenius equation. So although it's not immediately to see where this factor comes from, every physicist knows this fact. This comes from Boltzmann's statistics. So it basically says that you know that if you have a thermic system in thermal equilibrium, the probability that you find it with energy E must be proportional to e to the power minus z over kT. So what's the connection with chemical reactions? So that two molecules will react, we have to break some bonds. There's a typical energy that you have to overcome to actually produce the reaction. So if we ask ourselves the question, what at a given temperature, what is the fraction of particles that have an energy higher than a given energy. We call this activation energy. You get this factor. And it's not surprising that the rate of the chemical equation only depends on the ratio of the activation energy and the temperature. The temperature is the average energy your particles will have. So now the connection with the frequency of the chirps. We expect that the faster the chemical reactions are, the faster he will move his wings. So the frequency of each chirp will increase. He'll do more chirps in a unit of time. So you can connect the two by this equation. If you take the logarithms, we get this dependence. And the factor 1 over t as the activation energy. So this will be good to determine the activation energy. So some experimental data just to check if things fit. So this is the linear fit, the Dolbear's law. It's not so bad, but we see that there's some curvature in the data. And this is a better fit. Let's get more deep in this analysis. We linearize the data, and we obtain this dependence, as expected. So we can find what is the value of the activation energy. So now we must ask ourselves the question, is this just a coincidence? By the fact that the frequency of the chirps follows this law doesn't mean that it is this law. There could be some other effect that leads to this law. But we actually have another way to check if this is the case. So we calculate the activation energy. We can compare to typical activation energies that we find in reactions in the responsible for the muscle contraction. And the fact is that the value is good. It's of the same order of magnitude that of the known values. So I like to conclude. We have understood why the crickets work as thermometers and the process behind it. The frequency of the chirp is a macroscopic effect of some deeply complicated and microscopic physics that's happening in the interior of the insides of the cricket. And I hope when you are in a summer night, very hot, and you are listening to the crickets, you can calculate the temperature and show off using physics. Okay. So any questions?
Did you get those types of crickets in Canada?
I think I read you can find it in the US, so they can travel to Canada, I guess. So it's called the snow tree cricket. It's that green one. Anyone has ever seen this here in Canada?
So just a trivial question. If you were to plot the frequency versus 1 over t, you're saying it would just be straight.
Yeah, it was. Wasn't it?
You just showed the curve. Oh, right. Okay, sorry.
Yeah, the points are deviating due to my inaccuracy because I copied from a graph the points. And it's just to get an idea that this works. It's not rigorous analysis of that.
Do you know if anybody studied the same thing for frogs or birds or creatures?
No, I heard they studied that for the velocity of the ants. I think they are also this mechanism is behind that also. But it's the only example that I know apart from the cricket. Okay.
Other questions? Okay, then I'll thank the speaker. Oh,
no question. It was just a question answer. Because I think for amphibians it's a little bit more difficult. Because, as you said, for crickets you have to use the snow tree cricket that it works. And with amphibians it's far more difficult because they have mating behavior, then they use different velocities. So I think it won't work because of these conditions.
Yeah, my question was whether it still works despite the fact that it's much more complicated and the physics may be different and whatever. But it still may work, right?
The problem is that there are other effects as well. So if there is a partner nearby or an enemy or something like that, and you would have to take that into account as well. And I think that would be pretty difficult just sitting on a lake or something.
Any other comments? Okay, let us take the speaker.